Hello! In this video, we are going to prove the following theorem. The set of natural numbers is an inductive set, and the set of natural numbers is a subset of every inductive set. Now, the principles we're discussing in this video are based on Enderton's book on elements of set theory, and I'll leave a PDF version of that book in the description below. So first, let's remind ourselves of some definitions. If A is a set, then the successor of A is given by the union of A and the singleton set of A. And next, a set I is said to be an inductive set if the empty set is an element of I, and for every set A in I, the successor of A belongs to I as well. And a natural number is a set which belongs to every inductive set. And now, at this point, we have proven that there exists a set whose members are exactly the natural numbers. And the symbol we give for that set is omega. So now, let's get into proving this theorem. To start on the proof, we're first going to prove that omega is an inductive set. And in doing so, well, we're replacing I with omega. And so first, we want to show that the empty set is an element of omega. To show that the empty set is an element of omega, it suffices to show that the empty set belongs to every inductive set. Because if the empty set belongs to every inductive set, that means the empty set is a natural number, which means the empty set belongs to omega. So to prove that the empty set belongs to every inductive set, let's give ourselves an arbitrary inductive set. I'll call it I. Well then, by definition of an inductive set, since I is an inductive set, this means the empty set belongs to I. So what we've shown here is, if I is an arbitrary inductive set, then the empty set belongs to I. Since I was arbitrary, this shows that the empty set belongs to every inductive set. And because the empty set belongs to every inductive set, well then, by definition, that means the empty set is a natural number. And since the empty set is a natural number, that means the empty set must belong to the set of natural numbers, omega. So that shows the empty set is an element of omega, so the first condition is true. Now we want to verify that the second condition is true. So we want to prove for every set A in omega, well then the successor of A also belongs to omega. So to prove that, let's give ourselves an arbitrary set A in omega. From here, the whole goal is to show that the successor of A belongs to omega. In other words, it suffices to show that the successor of A belongs to every inductive set. And to prove that, let's give ourselves an arbitrary inductive set. I'll call it I. Well, since A is an element of omega, this means that A is a natural number. And so A belongs to every inductive set. So in particular, A must belong to the inductive set I. But then, by definition of an inductive set, since I is an inductive set, well then that means if we're given any element of I, its successor must also belong to I. So since A belongs to I, the successor of A must also belong to I. So we have shown, if I is an arbitrary inductive set, then the successor of A belongs to I. Since I was arbitrary, this shows that the successor of A belongs to every inductive set. And that's what it means by definition for the successor of A to be a natural number, so the successor of A must belong to omega. And so putting this all together now, we see if A is any element of omega, then the successor of A must also belong to omega. So that verifies the second condition holds as well. So we have verified both these conditions hold for omega, so omega is an inductive set. So now, we're going to prove that omega is a subset of every inductive set. In other words, we're trying to prove for every inductive set I, omega is a subset of I. So to prove that, let's give ourselves an arbitrary inductive set, I. From here, we want to show that omega is a subset of I. So to prove that, let's give ourselves an arbitrary element of omega. I'll call it x. Well then, this means that x is a natural number. So x belongs to every inductive set. So in particular, x belongs to the inductive set I. And so what we've shown here is if x is any element of omega, then x belongs to I. So omega is a subset of I. So we have shown if I is an arbitrary inductive set, then omega is a subset of I. Therefore, omega is a subset of every inductive set. And so this completes the proof. Now, a result that follows is the principle of induction, which says the following. If S is a subset of the natural numbers, and S is an inductive set, then S is equal to the set of natural numbers. And to prove this, well, the idea is, since S is an inductive set, and the set of natural numbers is a subset of every inductive set, well, in particular, the set of natural numbers is a subset of S. But then, since S is a subset of the natural numbers, and the natural numbers is a subset of S, these two inclusions imply that S is equal to the set of natural numbers. And so this completes the proof. And so yeah, that's pretty much it for this video.